Okay, you can start. Thank you.
Okay. Can you see my screen now?
Yeah.
Okay, so in fact, I was supposed to speak about electromagnetic absorber materials, but when I start to prepare my lectures, I found that this title is not fully correct. I just said one preposition, and now it is electromagnetics of perfect absorbers or absorber materials, because it's important to understand that when we are speaking about some wanted electromagnetic response, for instance, perfect absorption or something else, we should always remember not only about the material properties, but also about the geometry. So normally when we're speaking about absorbing materials, we always have in mind that it should be organized in so-called Salisbury screen ideology. So the dielectric material should have the thickness proportional to the odd numbers of 1/4 of wavelengths and things like that. That's why I don't want to speak only about the electromagnetic properties of the materials. I want to speak about the electromagnetic properties of the devices. That's why I decided to cut my presentation into two parts. The first one of today will be about geometry mostly, and the second one of tomorrow will be mostly about the electromagnetic properties of the materials. In fact, when we think about the absorbing materials, we should remember not only about the absorption properties, which may come from many of different physical reasons, like ionization, magnetization, or simple heating of the media. We should also remember about the suppression of reflection ability of material, which comes, as I already mentioned, from the geometry of the material and how it's organized. And always it's very important to have either perfect or broad bandwidth materials, and we should also remember about the different angular responses it could appear for the different polarization of the electromagnetic waves. And finally, as we are in the 31st century, we always should remember that all the wanted electromagnetic response should appear for as thin and as light material as possible. So we should also remember about the thickness and the weight of the material we use for the device fabrications. So first of all, the main question now, our motivation. What is our target? Why we are interested in electromagnetic absorbing materials? This is because the absorption of the electromagnetic waves underlies many of electromagnetic devices, like shielding layers, different types of detectors like field effect or acoustic type or bolometers. It is also necessary to produce filters, polarizers, collimators, and lenses. If we speak about 3D geometry, we always remember about the lightest possible waveguide and concentrators of the electromagnetic energy in order to produce electromagnetic logics, for instance, and also about the electromagnetic black holes. So many of applications are needed, and for many of these applications, we are thinking about the absorption of the electromagnetic waves. So before to start with the main content of my presentation, before to go into the possibility of use plain 2D and volumetric 3D geometry in order to produce different electromagnetic devices, working on the principle of absorption of electromagnetic waves, I want to stop very briefly just to remind you the fundamentals of the electromagnetic theory, which is Maxwell's equations and constitutive relations and boundary conditions. And also I want to talk very briefly on very specific case, which is thin conductive films, which is really very interesting for producing perfect broadband and of course very thin electromagnetic absorbing devices. So, as we know, the propagation of the electromagnetic field is governed by the Maxwell equations. The first two are so-called Gauss losses for electric and magnetic fields. The first one says us that the source of the electric fields is electric charges. The second one says us that there is no magnetic charge in nature. Then we also have Faraday's law of magnetic induction and Ampere law, which in fact establishes the charge conservation. And also it says us that the displacement current is very essential in order to predict the propagation of the electromagnetic wave. So as we already know, the sources of the electric and magnetic fields are charge and currents respectively, and they generate the fluxes of electric and magnetic fields. But these fluxes are not observable. And in order to come to the observable things like electric and magnetic fields, we need to understand where our electromagnetic wave propagates. So we need to remember about that our electromagnetic wave could propagate in some matter. And the Maxwell equation doesn't give us the response, doesn't give us the answer, how to connect this unobservable electric and magnetic fluxes and observable electromagnetic electric and magnetic fields. The answer to this question gives us the constitutive relations that connect fluxes with the electric and magnetic fields through the dielectric permittivity and magnetic permeability. So in fingers, we could think that this permeability and permittivity say us how effectively the matter interacts with the electromagnetic field and what the perturbation includes into the matter. What is interesting that even if we speak about the interaction of electromagnetic fields with vacuum, we don't have zero values for the permittivity and permeability. In fact, if you dig deeper and deeper, you would understand that the reason for that comes from absolutely other science, which is quantum electrodynamics, which say us that when the electromagnetic field propagates in vacuum, it distributes and perturbates the vacuum, and pairs of electrons and positons appears and annihilates. And this interaction comes with a particular speed, finite speed, which is the speed of light. That's why the permittivity and permeability of free space, or permittivity or permeability of vacuum, is related to the fundamental constant, which is the speed of light in vacuum. When we deal with anisotropic media, we should remember that the permittivity can have the tensor form. In case the permittivity is dependent on the intensity of the applied electric field, we deal with a nonlinear material. And finally, what is very important, that most of the materials are dispersive, which means that the permittivity of this material is very dependent on the frequency range. That's why every time when you speak about the electromagnetics, you should remember to address particular frequency range. For instance, tomorrow we will speak about the percolative properties, but they make sense only at zero or very low frequency, when the particles inside the composite material should touch in each other. But when we switch to the higher frequencies, these different parts of the composite material start to feel each other electromagnetically through this so-called electromagnetic coupling, and we should not take care very much about the percolation processes. So the dispersion is very important. What is also important when we analyze the propagation of the electromagnetic wave is to understand what happened in the interface between two media having two different permittivity and permeability. So for this, we should remember about the boundary conditions. Boundary condition also should remember about the fact that electromagnetic field is transverse field, which means that electric and magnetic components oscillate in the plane which is perpendicular to the direction of the electromagnetic field, and that's why we could state in the very general way that the tangential component of the electric field continues across the interface, whereas the difference between the tangential components of magnetic field give us the surface current. In case we deal with a perfect conductor like perfect metals, which in fact could not exist in the nature, we expect that this material does not allow the penetration of the electromagnetic field inside. That's why the tangential component of the electric field of the incident electromagnetic wave will be equal to 0, and the tangential component of the magnetic field of the incidence wave will be equal to the surface current generated on the surface of the perfect conductor. Of course, as I already mentioned, there are no perfect conductors in nature, and all conventional conductors allow some penetration of the electromagnetic field inside the conductor. And these very small depths where the electromagnetic field could penetrate inside the conductor, called skin depths. It is inversely proportional to the conductivity of the material, and also it is inversely proportional to the square root of the frequency, which means that the larger the frequency, the smaller the skin depths will be. And at certain frequencies, like for instance for X-rays, we will have almost invisible skin depths for most of the known conventional metals. If we compare the skin depths for instance, kappa in the two different frequencies, 2.4 and 5.5 gigahertz, you will see that the electromagnetic field could penetrate into the kappa up to 1.3 microns at smaller frequency and less than 1 micron at higher frequency. So when the electromagnetic wave interacts with the matter, it will undergo the absorption, which is the quantity explaining us how the electromagnetic energy of the electromagnetic wave will transform to the internal energy of the absorber, like for instance the simple thermal heating, as in most of the known cases, known also as Joule heating or ohmic losses. And also it will depend on the refractive index of the media. When we deal with bulk metal, bulk means that its thickness is much larger than the skin depth, we expect to have so-called mirror reflection, when the angle of the incident wave will be equal with the opposite sign to the angle of the reflective wave. However, when we deal with the dielectrics, they support not only the reflection of the electromagnetic waves, but also the refraction, which in its turn is a subject of, could be the subject of substantial absorption, which we are looking for when we are dealing with the electromagnetic materials for absorption application. And this reflection and refraction is dependent on the permittivity of both medias, and also depending on the incidence angle, and could depend very much on the polarization of the radiation that come into the interface between two media. So now I come to the simple classification of the materials based on the permittivity, the imaginary part of the permittivity, which is directly dependent on the conductivity of the material. It is responsible for the losses, for the absorption of the material we deal with. So for the perfect dielectric, we have zero conductance, and this is lossless medium, but it is almost does not exist, let's say. For the materials with very small conductivity, where the ratio of imaginary and real part of the permittivity is much less than unit, we have either poor conductor or very good dielectric with low loss medium. When the real and imaginary part of the permittivity is almost equal, we have lossy conducting material and lossy propagation medium. And finally, if don't think about the case of perfect conductor, when we have good conductor, which means that the conductivity is very high, which means that the ratio of imaginary part and real part of the permittivity is much more than unit, we come to the high loss medium, which is in fact exactly what we are looking for when thinking about the electromagnetic material for absorption application. So just to summarize with very simple slide, if we deal with the perfect conductor or just a conductor in bulk, when the thickness of the conductor is much higher than the skin depth, we will have reflective media. When we have non-perfect conductor, which allows the penetration of electromagnetic field inside, we might have very small absorption, but all the rest of the electromagnetic radiation will be reflected. And finally, when we deal with the dielectric medium, we might have substantial losses due to, for instance, Joule heating. But when you have dielectric, as I mentioned from the very beginning, you always should remember about the geometry of this sample. If, for instance, the geometry will allow us the constructive interference, when the incidence wave will be interfere with the reflected wave from the top side and the bottom side of the device, this dielectric device, we could come through the constructive interference to the wanted electromagnetic response, either to suppress fully the reflection ability of this material or to enhance fully up to the 100% of the reflection material of this particular directed slit. So again, if we want to have wanted electromagnetic response, we should remember not only about the material properties, electromagnetic properties of the material, but also we should remember about the geometry. So always think about the device. And there is really exceptional case, the case of thin conductive film, which thickness is much smaller than skin depth. And if we address the wavelength, which is much larger than the film thickness, and this film is made of highly conductive material, we could expect for particular thickness very interesting electromagnetic response. The classical electromagnetic says that for thin conductive film, which thickness is inversely proportional to the conductivity of the film, for particular thickness, we could achieve 50% of absorption of electromagnetic radiation, 25% of reflection, and 25% of transmittance. So again, remember that in order to absorb substantial amount of electromagnetic radiation with a dielectric slab, you need to come up with 1/4 of wavelength at least. And here When we speak about thin conductive film, you could absorb for freestanding conductive film 50% of electromagnetic radiation, just having something of invisible thickness. That's why it brings us to the idea why not to try with graphene. Why graphene? First of all, graphene is very absorptive even in optical frequency range. Game and Novoselov were given by the Nobel Prize not only because they demonstrate in practice that 2D crystalline material could be thermodynamically stable and could exist in nature in freestanding way, but the most important issue is that they analyze the optical and electronic properties of this new 2D material. For instance, they visualize the thin constant alpha. Using the graphene, they demonstrate that one graphene layer could absorb pi alpha of the electromagnetic radiation, which is 2.3% of the radiation, and this is due to the interband transition between the within the conduction band. But of course, we could expect that if we deal with the intraband transition, which refers to the terahertz and to the microwave frequency ranges, we could expect to absorb more, even much more than this golden 2.3% of the electromagnetic radiation. So why graphene? Because it is highly absorptive, even in optical frequency range, and we could expect that it will be absorptive also and much more absorptive in terahertz and microwave frequency range. But also it's very easy to tune the electromagnetic response of graphene because it's the electronic structure composed such a way that the valence and conductive band touch each other. So it means that any external force, like small mechanical deformation, even just when you put your graphene into some substrate, or electrostatic doping, or highlighting graphene with optical or some other radiation, will give a substantial change of the position of the Fermi level, which means that you could have either almost insulating material or the material with very high conductivity. So again, why graphene? It is highly absorptive and it is highly tunable. And also, of course, when you think about the optical frequency range, it is almost transparent because this 2.3% of the radiation which graphene absorbs in optical frequency range is almost invisible to our eye. However, remember that this 2.3 comes from the single atomic layer, which is incredibly high amount of electromagnetic radiation from the other side. But for practical application, it's important to understand that this is almost transparent for the optical radiation. Another important issue is that in contrast to almost all other known materials, graphene is non-dispersive in microwave and terahertz frequency range because according to the theoretical calculations, its conductivity, both imagery and real part of the conductivity does not change in very wide frequency range from 1 Hz to 2 terahertz. So we decided to try this graphene. What equivalent electric circus technique could say us? If you want to absorb as much as possible electromagnetic radiation with thin conductive film in free space, its conductivity should be equal to the admittance of free space twice. What is interesting about graphene and why we start to think about graphene? We found that the conductivity of the sheet conductance of high quality graphene, like exfoliated one, is almost equal to the admittance of free space, 2.5 versus 2.7. So it looks like you need just 2 graphene layers in parallel in order to achieve this admittance matching condition. So you could absorb 50% of electromagnetic radiation when you have just 2 graphene layers of proper quality. Of course, when we are thinking about practical applications, it's better to switch to the graphene which are made in laboratory and not just exfoliated like chemical vapor deposition graphene. I don't have too much time to go into the details. I just want to say that it's already now possible, and many teams in the world are able to grow high quality graphene with very large grains and thereby with very large conductivity and other important properties for the electromagnetic applications. But what is not very good is that for handling this graphene, for transfer it, you normally use the different layers of thin polymers in order to transfer it, and if you need a number of graphene layers and to stack them into the sandwiches, you will need this thin layer of polymer every time. But what is good about our application, if we speak about microwaves on terahertz frequency range, this 100 nanometers of polymer is invisible for the electromagnetic radiation of these frequency ranges, because 1 terahertz corresponds to 300 of microns wavelengths, 30 gigahertz correspond to 1 centimeter. So if you compare it with not very lossy material, which thickness is less than 100 nanometers, you could forget about that. Moreover, this thin layer of polymer allows us to decouple the graphene layers one from each other, and we could treat the conductivity of the overall sandwich structure as the conductivity of one graphene layer multiplied by the number of layers. What is also important is, of course, if we speak about freestanding graphene or 2 graphene layers, it is incredibly absorptive. It could absorb at proper conductivity up to 50% of electromagnetic radiation. But for many of device applications, you will need more. You will want to have perfect absorption. And there is a very simple way of achieving this perfect absorption by thin layer of metal or thin layer of number of graphene layers, is just to put this graphene in between 2 dielectric media. And when radiation comes from the side with a higher reflective index, you could achieve very high absorption, almost perfect absorption with this one graphene layer. So now I come to the original results that were collected in our teams, both in Minsk team in the Nanoelectromagnetic Lab and in the University of Eastern Finland, who provides us with particular experimental samples. So we found that it is really the case when we deal with graphene of not so perfect quality as the exfoliated one, but good quality, like our CVD graphene, we will need not 2, but 4 graphene layers stacked to the sandwich structure in order to achieve this golden 50% of absorption of electromagnetic radiation. But immediately we start to think how to enhance this absorption ability, and the simplest way, of course, is to put this graphene sandwich structure into the top of the dielectric slab, which correspond to the quarter of wavelengths, and according to the both theoretical estimations and experimental data, with this we could go up to almost perfect absorption. We experimentally observed more than 80% of absorption for the sandwich composed of 4, 5, and 6 layers. If you want to increase even more, and also to reduce the thickness of the used dielectric in order to work with just a few tenths of microns and not the millimeters. If you address the microwave frequency range, you should add to the story also back reflector, of course not perfect one, as we already know that they not exist, but thick enough in order to be thicker than the skin depth in order to provide us with this constructive interference. With this, we could achieve perfect electromagnetic absorption at many thicknesses of this material corresponding to the odd numbers of quarter wavelengths. If you don't want to have perfect absorption, but you want to address the broadband absorption, maybe not so perfect, but still high, you could organize the sandwich structure and again put it into the top of the back reflector. And when the radiation comes from the graphene side, you will have, this was achieved experimentally, you could have the absorption at the level of 90% for very broad frequency range. Here, for instance, from 10 to more than 15 gigahertz. So with this ideology, we were able to propose the first application of the high absorption of the electromagnetic waves, which is shielding devices of the optical window for the optoelectronic devices. So when the radiation, the radio frequency microwave terahertz comes from the dielectric window size, it will be absorbed by the graphene multilayer, and then the optoelectronic devices will be safe and uncoupled with the electromagnetic radiation from the outside. Another interesting application for the same material, graphene being put on the top of the dielectric of proper thickness, which provides us with almost perfect absorption, is optoacoustic detector for high power microwave and terahertz pulses. First, the radiation comes from the window side. It will be absorbed in the graphene layer, which leads to the heating, so the Joule effect, and this heating generates the acoustic wave that already will be detected by the detector of acoustic pulses, and there will be the time delay between the pulse and between the detection of this acoustic pulse, which is very good because there exists a terrible problem of detection of high power pulses of microwaves and terahertz. So this ideology could be easily applied for this particular case. Then it's important to understand that this optimal thickness corresponding to this golden 50% of absorption of the electromagnetic radiation is very dependent on the polarizability of the incidence radiation, and for the S polarization, this optimal thickness is proportional to the cosine of the incidence angle, whereas for the P polarization, this optimal thickness is inversely proportional to the cosine of the incidence angle, which means that for the S polarization, we could achieve the absorption of 50% of electromagnetic radiation with almost invisible thickness. And in fact, it's quite clear from the general point of view, because when you have almost oblique incidence, it means that the effective path of your electromagnetic waves through the media, through the thin film, became larger and larger. And finally, you need just very invisible thickness in order to achieve 50% of electromagnetic radiation. And this is exactly what we observed experimentally. This experiment was done for the graphene being put on the top of 0.5 millimeter silica substrate. And you see that for the S polarization wave, you could observe the change of transmittance from 70% to almost zero when you change the incidence angle from normal incidence to quite oblique one, close to the 70 degrees. So we propose to use this interesting property in order to fabricate the polarizer for the microwave and terahertz radiation based on graphene. When the radiation come on the graphene plane on the top of thin dielectric, you could collect the depolarized wave here. And after the mirror, you could collect the S-polarized wave here. So this is really good and very effective polarizer for the electromagnetic waves of terahertz and microwave radiation. Another important story comes from the tunability of graphene. Remember that you could tune the Fermi level and thereby the conductivity of graphene very easily. And the simplest way, of course, is just biasing. Here I present you the results collected for graphene being put through the thin slab of the dielectric on the top of the reflector, and the radiation comes from the graphene side, and through the constructive interference, as I already mentioned, you could achieve either perfect reflection or perfect absorption, and of course we are interested in perfect absorption. But in order to tune the position of this absorption peak, you just need to bias graphene. And when you change the conductivity of graphene, the position of the perfect absorption peak will tune. Another possibility to tune the perfect absorption of graphene is simply to put graphene on the top of flexible and stretchable substrate, like for instance polydimethyl siloxane, and just through the mechanical deformation you will change the thickness of the layer on which you have your graphene, and with this you could easily tune the position of the absorption peak. For instance, we demonstrate that changing the thickness of the PDMS from 100 micron to 100 micron and 120 microns leads to the change of the position of the absorption peak from 1 terahertz to almost 0.6 terahertz. What is also important that here we speak about quite high frequencies, which means that we should not take care a lot about the how or what would happen if graphene will be broken during this manipulation with the stretching of the polymer. These small pieces of graphene will feel each other electromagnetically, and we demonstrate both through theory and experimentally that up to the 30% of the deformation of the polymer where graphene is lying on top of, we don't see any serious substantial difference in the conductivity of the graphene. So we could stretch it and de-stretch it many times, and every time we will come to the same results for the tunable graphene perfect absorption. And one more really interesting way to tune the electromagnetic absorption of graphene is just to highlight the graphene layer with the infrared beam. And because of this infrared will generate the hot carriers, and this will lead to increase of the electronic temperature, and the scattering rate will substantially increase, which leads to the suppression of the conductivity and thereby suppression of the absorption ability. But what is really nice here is that these processes are really fast, ultra fast. In order to change, to modulate the amplitude of the electromagnetic wave, in order to change the absorption from 80 to 40, you will need less than 3 picoseconds of radiation with the infrared beam. And finally, in order to finalize the story about graphene, as we are speaking with the electrical engineering and mechanical engineering, you always think about how to switch from the laboratory to industry, what to do if we want to have really good devices, how should we control the quality. What is really good about graphene for these particular applications, for microwave and for terahertz, is the fact that Even if we deal with not very high quality graphene with a lot of defects like the embryos of next layer CPS or holes in the CVD, typical CVD graphene of not very high quality, our electromagnetic response will not feel the difference when the fraction of the defects is less than 10, to be honest, less than 20%. So it means that if you will deal with the quite high quality graphene, but it will compose holes here and there, or the embryos of the new layers, which normally happen to the CVD graphene, you should not take care about this because the electromagnetic response will be the same. And this is not only the theoretical estimations made using the rigorous coupling wave analysis, this is also the result of our experiment when we compare the graphene composed of two different grain sizes, small 20 microns and large 400 microns. And of course, the number of defects will be very different in this type of graphenes because the defects, for instance, is the grain boundary, and we see that for the optimal configuration composed of from 3 to 6 layers of graphene, we don't see any difference in the electromagnetic response, not only theoretically but also experimentally. So concluding this, we have just 10 minutes. Concluding this first part of my presentation, I must say that this thin layer ideology, this ideology that could be applied for a few layers of graphene, is very interesting to get high absorption ability, playing with back reflectors, with proper dielectrics of proper thicknesses. And with this, we propose and realize a number of terahertz and microwave phased devices such as shielding layer, ultrafast modulator, polarizer. Detector have not been realized yet, but we are thinking about that, and perfect tunable absorbers. So now I come to the ideology of 3D architectures. Of course, when we speak about the bulk material, the only you could play is, let's say, the thickness. But if you have some analogy with sponge which could absorb water, if you put it into it, you could think about something very similar for the electromagnetic waves. If you will deal with the material with open porosity and the pore size will be compatible with the wavelengths, you could expect that at certain conditions this material will be highly absorptive. So when the electromagnetic wave will come into this material, it could never come out. For that, you should use either the skeleton with the thickness much smaller than the skin depth, like it was done for the graphene, and they exist graphene forms, but we will not concentrate on it today. For this, you could play with the material which pores, and also when we deal with the open porosity, the window size through which this material is connected to each other correspond to the wavelength applied. So I just want to tell you that if you deal with material of composed of the cells with open porosities, if you address the electromagnetic wave which correspond to the cell size and window size, you may expect to have resonance behavior, electromagnetic behavior, like for instance resonance electromagnetic absorption. But you should also remember about the conductivity of the skeleton and the thickness of the skeleton visit. Of course, if the skeleton is too thick and the material is too conductive, it will behave as a bulk metal. In order to play with 3D geometry, we propose two approaches. We could deal with the fully carbon periodic lattice composed of highly conductive skeleton, or with the periodic lattice, which skeleton is made of the composite based on carbon and with intermediate conductivity from 0.1 to maximum 200 Siemens per meters. And today I will try to tell you about the possibility to use fully carbon highly conductive skeleton. And tomorrow, when I will speak about the composite materials, I will stop briefly on the second approach. So for fully conductive skeleton, normally people use 3D printing. This is stereolithography, and when you impregnate this beautiful structure with some catalyst and pass through the pyrolysis, you could carbonize the structure, and during the carbonization of the structure, the shrinkage could appear, and this lattice will not be fully symmetrical anymore. This gives us the idea why not to use this material as a photonic crystal. And modeling says that at certain frequency, which is called plasma frequency, the behavior of this material could be fully changed from fully reflective to fully absorptive. And this is exactly what we observe experimentally for this particular cubic fully carbon lattice. So we see that when the radiation, when the electromagnetic field is along the x direction, this is almost fully reflective structure, whereas when the electromagnetic field is parallel to the y direction, at certain frequency, absorption increase up to the almost perfect. And this frequency is correspond to the cell size of the structure or to the window size where these cells are connected to each other. The smaller the cell or the window, the larger the absorption peak frequency. But what is really nice is that this simple and beautiful 3D printed structure behaves like the waveguide because it allows propagation of the electromagnetic waves only up to the certain frequency, and after that the electromagnetic waves will be fully absorbed. Also, it allows us to concentrate electromagnetic wave periodically, and this concentration and the frequency corresponding to the concentration will be again very dependent on the cell and the window size. And if you are able to change the dimension, like for instance, just simple pressing, mechanical pressing, which is possible for the case of the graphene forms, you will change immediately the position of the absorption peak where you could concentrate the electromagnetic wave periodically. You could also fill your open porosity structure with different dielectric media, and this will allow you to switch substantially the position of the absorption peak. Like for instance, for this particular case, when you fill the structure with the dielectric media with the permittivity from 2.5 to 4, you will change the position of absorption peak from 40 gigahertz to almost 30 gigahertz. And I already don't have time to speak about the combination of 2D and 3D geometries, but I will try to come back to that tomorrow. So my main conclusion from today's presentation is that both material properties and geometry are very important in order to achieve wanted electromagnetic response. And graphene, being exceptionally tunable and highly absorptive in microwave and terahertz frequency range, could be used in both cases for 2D plane geometry and also to be organized into the volumetric space. So thanks a lot for your kind attention.